To paraphrase the Bard, to explain or to predict? That is the question. Okay, that's not really the question that Galit asks, but it is very close. She wants us to think hard about, are we building models to predict, or are we seeking explanation? There's a very important distinction there that she's going to talk to us about. Galit Shmueli is a distinguished professor at Tsinghua University in Taiwan, and she has written extensively about this subject of the difference between explanation and prediction. She's also a highly acclaimed author. She's written 2 books, including one with our keynote tomorrow, Ron Kennett, and here to explain to us the difference between explanation and prediction. Please welcome Galit Shmueli.
Okay. Thank you very much for the kind introduction. I'm very pleased to be talking to such a large audience with so many people who actually do data analysis and who have a statistics background or statistics affiliation in this way or the other. I've presented this talk in many different audiences, and there's a completely different reaction in different audiences. So I'm always curious to see what's going to happen here. So as Jeff said, explaining or predicting is really the topic of this talk. And I hope that at the end of it, you'll come out with lots of thoughts in your head about what you've been doing and the types of things that you do and trying to analyze what's going on here. I have to warn you, I'm going to go through a whirlwind of things. There are going to be so many things going on. My slides are always available. The papers are there. Thank you. And you can always follow up later. I'm very good on answering. So excuse me if I rush through many things, but there's an interesting story here, and I have to kind of run you through it. What you can see here on the slide are 2 pictures that have one theme. And I think the theme is kind of easy now. Yeah? Can anybody guess what the theme is? Okay, it's a newspaper, yes. And the point is that we're talking about a tool or an instrument or something that we're using, but we utilize it in different scenarios in totally different ways, and we require completely different qualities of that tool. For example, if I'm going to be reading the newspaper in the morning, I really want the news to be fresh and accurate, and maybe I want the format of the newspaper to be comfortable to hold with my cup of coffee and not get ink all over my fingers. Whereas if I'm going to be using it for wrapping food or wrapping fish or chips or whatever it is, I have completely different qualities that I care about. I don't care if the news is fresh or not. I want the paper to be very nice and absorbent of all the grease. So it's the same newspaper, but I'm using it and needing it for completely different goals. And that's really how I'm thinking about data analysis and modeling. We can use the same tools, same toolkit, even the same model, even the same data, but we will be using it in completely different ways if we're going to be using it for causal explanation, whereas as opposed to prediction. So let me walk you through this whole story. Before I do that, I'll give you a tiny bit about my background so that you can, the first question that people ask me is, how did you stumble upon this? How did you even get to this? And here's the answer. I had to make a very, very slim map of the world because I had to cover all of it. And this is where I came from and kind of where I learned and where I worked. I started in a very small country called Israel. And that's where I studied, and I was in the Israel Institute of Technology at the Technion. And that's an engineering school. I was in the IE department. And my PhD is in statistics, but I was around engineers, so I was kind of an engineering mind person, and my work was about industrial statistics and process control. And after I graduated, I moved to Carnegie Mellon University in Pittsburgh, in the United States, and there I moved into a department of statistics that is housed in the Social Sciences College. So now I'm working with people who are, either I was collaborating with people who were doing marketing in the business school, I was working with statisticians in the department, I was working with people working on biosurveillance, so epidemiologists, and now it's a completely different set of people that I'm teaching also. After 2 years, I moved to University of Maryland, pretty close, and there's the first time I moved into a business school. And an engineer who moves into a business school has the shock of their life. It's a completely different audience. Your colleagues are different. Your students are different. Everything is different. And that's where I start collaborating with folks in information systems who come with backgrounds of either economics or behavioral sciences or computer science, kind of a mixed group. And I've worked there for a long time, working a lot in online auctions and e-commerce, and of course doing a lot of statistical methodology stuff, but the applications were in information systems. Then I take a sabbatical and eventually move to Bhutan, which is a small country in the Himalayas. And I spent about 5 years there, living there, and during the winters, working at the Indian School of Business in Hyderabad. And in Bhutan, we were co-directing a lab that was helping with technology and education. So I had a dual life implementing things, and also being a faculty member in the Indian School of Business. And this is kind of when the boom of big data and everything reached India. It was just beginning in India. So I was kind of following it from where it was going and helping designing programs and teaching the people who were eager to get into this whole space. And finally, 3 years ago, I moved to Taiwan, and that is where I am right now. And big data is kind of just beginning there. So this is very, very interesting. And there I'm in an Institute of Service Science, which is in the College of Technology Management. So now you get a little bit of an overview of where I came from and the diverse places, both geographically and professionally, that I've been in. And from here, it started raising a lot of questions in my mind. I was seeing that people who were not statisticians were using statistics or data mining pretty heavily, but in ways that are completely different than the ways we were taught to learn it and teach it and use it. And that's where Explain or Predict started bubbling up, and you can see where it's been going. A brief thing about my work, people ask me, so what is your research? I can't really characterize my research. I just call it entrepreneurial statistical and data mining. A lot of it is methodology. It's driven by applied problems. Some of it is applied. I do a lot of interdisciplinary work with people in lots of different disciplines. And what I like to do, what I've been doing mostly in the last few years, is statistical strategy, and Explain or to Predict is one example. When I say statistical strategy, what I mean is how do researchers use statistics outside of the field of statistics? And that's where a lot of work happens, and information quality is work that I'm doing with Ron Kennett, who's giving a talk tomorrow. A few of my books are up here. You might know the Jump book that came out recently, the big gray one there. And our newest book that came out is Information Quality, which we will be talking about tomorrow a little bit. There's also, I've been involved in MOOCs that are teaching these types of topics. And that's me in a nutshell. Now let's get back to Explain or Predict. So here's how I'm going to go. First of all, I have to talk about definitions. And although I'm guessing everybody here has touched data, we all come from slightly different backgrounds, and definitions can be really, really critical. I'm talking about very simple definitions, such as a model. The word model means completely different things to different people. And in fact, one of my ex-students from Maryland is now a model in New York. So what I'm going to do next is, after I talk about definitions, I'll give you a little tour of the social sciences and how they use statistical modeling. And I'll show you how that field is really dominated by causal explanation. And to get an idea of what it means there, I'll show you just a very, very prototype type of work. And it's very different from DOE, if that's what you're thinking. Then I'll make my first point. I have 2 points to make. One is that explanatory modeling, the whole process that you'll go through, is completely different than predictive modeling. That's going to be the first point, and I'll try to convince you that that's true in a few different ways. And I'll actually show you the modeling paths and show you the many, many divergences that happen in every step of the modeling, so that at the end, I hope you're convinced. The second point I'm going to make is that explanatory power is different from predictive power. And many people confuse these two, and they think that if they have high explanatory power, then that means they also have high predictive power, and vice versa. So that's going to be the second point, shorter, but it will be there and prominent. And finally, if we get these 2 points, I'll talk a little bit about the implications of not realizing that these 2 points are true, and the kind of heavy price that we're paying both in academia and scientific development and in industry. Okay, let's start with definitions. Very simple, 2 slides. First of all, when I say explanatory model, I'm talking about a theory-based statistical model for testing causal hypotheses. When I say theory, it could be a theory in physics, it could be a theory in psychology, it could be a theory in economics. Choose your domain. But there is a theory behind the scenes. This is not a hunch, this is not a domain thing. This is a theory, a scientific theory that's going on. when I say explanatory power, what I mean is a strength of a relationship in the statistical model. So usually there'll be some kind of statistical model that's quantifying the relationship, and when we say, oh, this has high explanatory power, we mean that the relationship in this statistical model is very strong. In contrast, the orange says prediction. So when I talk about a predictive model, I'm talking now about any model or algorithm, empirical, that will be used to predict new records or new observations. And when I talk about predictive power, I'm talking about the ability of this model, or any other model, to accurately predict new observations. Realize that I can take an explanatory model and test its predictive power. Okay, so I have two things going on here that don't necessarily have to come together. All right, so with that in mind, when I say explanatory or predictive, this is what I mean. Here's the interesting story that I discovered. There's 3 different planets in terms of using data and data analysis. The social sciences are strongly dominated by causal questions. The types of research that people conduct in social sciences and in management and in marketing are about how does the world work? Why does this happen? How do things work? When you look at the world of machine learning, it's all about prediction. Oh, let's just get this new point predicted correctly. Everything is geared towards prediction. When we look at the world of statistics, it's kind of a bizarre world. It actually doesn't go too deep in here and not too deep in there. The big bulk of it is about description. We try to create these models that are nice, parsimonious descriptions of the world, and we're really afraid to say that they're causal, and many times we don't even use them for prediction. So there's 3 types of areas using data analysis for completely 3 different goals, and each one kind of lives in a silo. And when you start asking yourself, why is this happening? Why are they using models in this way and these people are using in that way? Then you start understanding that they're after different goals. Let me go through social modeling, social sciences, statistical modeling in a real small nutshell. First of all, here's the story. What they care about is testing causal theory. They have a theory, domain theory. They're going to use statistical modeling only for testing that theory, refuting it, improving it, okay? Then they're going to use some kind of statistical model that is not necessarily a causal model. They're not running a DOE. What they're doing is they'll use a regression, they'll use a path model, something that's capturing association. And based on that, they will decide whether the causal model is refuted or not. Okay? That's how things work. If you look for prediction, you won't have it. Now, just in the last few years, you might have a few daring people or high-level people who can actually publish that stuff show up. But you don't find prediction in those papers. If you see the word prediction in there, it's usually for predictor, meaning independent variable, or we predict that, which means we hypothesize that. The word predict does not mean here prediction in the term that I mentioned. Let me show you what a typical paper looks like, okay? This is just an example. I grabbed this little chart from the web, someone else. A classic journal paper, open any paper, any journal in psychology, information systems management, sociology, political science, choose your favorite, will look like this. There'll be some kind of a causal theory that will maybe be shown as a chart, like here, and you have the arrows. So the arrows means this causes that. It's very obvious. And what you see in those circles are not measurements. They're what we call constructs. They're abstractions. So in this example, you have economic responsibility, social responsibility, environmental responsibility, and those 3 things here are hypothesized to cause the service brand image. And then service brand image is hypothesized to cause these 3 outcomes: intention to continue to use some technology or something like that. So this is the theory. And then from here, there is going to be a hypothesis, and you see those H's on the arrows. H1, H2, H3, H4. In statistics, we stop at H1. And when I saw my colleagues doing H2, H3, H4, I was really puzzled the first time I saw it. But actually what's doing, it's conveying a bunch of different causal questions that are coming out of the theory. The next step that's going to happen that takes a long part of the paper is what we call operationalization. That's a really long word, too. And what we do is we take each of these abstractions, these constructs, and we have to figure out how to measure them. And that's a very careful and theoretical work and some empirical, and it's based on a lot of previous work that has been done. And after you establish, this is why I'm going to measure economic responsibility in this way, then you can actually move on, say, here are my measures, fit a statistical model, and then use that statistical model to test the hypotheses that we tested before. Okay, so the hypotheses are coming from the theory. The statistical model is really just used to test those hypotheses. Classic paper. Okay, so in short, in the social sciences and in management, data analysis, usually statistical models, are mainly used for testing causal theory. And if you ask them why, they'll tell you because if we can explain the world, we can predict the world. Actually, you'll hear a lot of people telling you that prediction, empirical prediction, the way we've talked about it, is not really scientific. And you'll hear that a lot, again, in the social sciences, but you'll also hear it from very prominent statisticians. Here's a quote from the late Emmanuel Parzan in Statistical Science, the famous issue that had the Bryman paper. And this was one of the responses, and he said, the two goals in analyzing data I prefer to describe as management and science. Management seeks profit, and science seeks truth. I followed up on this at the time, and I sent him an email, and I asked him, Emmanuel, do you mean prediction is management, and explanation is science seeking the truth? And he said, yes. So there's a very strong notion among academicians and researchers that prediction is for applications. It's very useful. You do recommender systems. You can get immediate value. But it's not something that helps you develop theory. And that's a very, very problematic claim. Next thing we did was we went and we looked at the information systems top literature. And the reason we did this was because I was going to publish a paper related to this in a journal in information systems. So this whole work was done in the domain of information systems, but actually it generalizes to any social science that you want. So we went there and we searched for all the possible articles that had the word predict, forecast, and whatever combination that you want. This was 1990 to 2006. And we asked ourselves, for each paper, we manually checked it. And we asked, did they actually state a predictive goal? Yes or no? Did they use predictive modeling? Yes or no? And did they actually evaluate predictive power? Yes or no? And the answer was kind of interesting. We found 52 predictive articles that actually had prediction in there that meant predicting. And here's what the results look like. So the biggest bar here is people who wanted to evaluate predictive performance. They said, this is how well our model predicts. But they didn't know how to do it. They were using maybe something like an R-square to do that. Then you had the second highest bar is people who wanted to do something predictive, but they didn't know how to do it. They were using their old explanatory toolkit to try and do something predictive. So there is interest in doing prediction here. But most of the people who want to do it don't know how to do it. Remember, this is 1990 to 2006. Things have slightly changed. Not a lot, but slightly changed since then. And then we have a few papers that actually did do things adequately. Okay, so from here what we learn is that some of them want to do it, but most of them actually don't want to do prediction. And I had so many conversations with colleagues. The ones who are most against prediction used to be, again, the world keeps changing so fast, are the econometricians, the people with the economics background. And they'll tell you a good explanatory model predicts well. If I understand how something works, I understand the causal mechanism of it, I can predict it. That's one claim. The other claim that I'll hear very, very often is you have to understand the underlying causes in order to predict. You can't just build a model and run it and get predictions. So those are the two claims that are happening again behind the scenes in the world of social science and management. Things are slowly changing, but as you know, the academic world is really slow to change. And if you want to make any changes, then you have to let people publish in top journals things about these topics. So there are two recent papers, these are just two examples of papers that are doing prediction in a scientific way, not so much for an application or a project, and we're able to publish them in the top 2 journals in information systems. Again, just 2 examples, and there are a few more coming out. There were a few special issues that came out, but this field is moving very, very slowly. All right, now, This was in academia. Now let's move to industry. In industry, we kind of have the opposite happening. In industry, the rush to prediction has gone crazy, right? When you say big data, it means prediction. What are people doing? Prediction. Here's a little interesting article that was published by Deloitte in CIO Journal. And there are a lot of companies who are now selling you software for what they call workforce analytics. And the goal there is to try and figure out who's going to be leaving you in your company, which employees is going to leave next, and catch them and do something with them, good or bad, I don't know, right? And like customer churn kind of ideas. And look at what they're claiming. So they're saying predictive workforce analytics software can help CIOs reduce voluntary turnover, blah, blah, blah. And then they say they collect a lot of data, including an individual's salary, size and date of their last raise, results of their most recent performance review, their tenure, amount of vacation in the 12 months, and the length of their commute. Okay, this is the kind of information that is captured by employee systems. I'm guessing you know about this as well, right? Okay, and then if you keep scrolling down, here's what they promise you. From these attributes, predictive workforce analytics programs generate a risk score for each employee, showing their likelihood of leaving during the next 6 to 12 months. Okay, this is predictive, right? But then look at what they're also promising you. They also highlight the top factors influencing employees' interest in leaving. So they built a predictive system. They're giving you predictive scores, like credit scores, but they're also making a very strong claim about, we'll also explain to you why. We can tell you exactly why this guy is leaving. It's not that their wife has moved to a different place or something like that. It's because the combination of salary and the number of... And if you compare this to what I just showed you is causal explanation and what hard work that takes to build a theory and to work through the whole story, they're obviously not really doing causal explanation. They're just claiming they are doing it. So in industry, we have the opposite problem. People are doing prediction and they think they're doing explanation, but they're not doing explanation. Maybe they're the same. Maybe I'm just driving you nuts here. All right, so let me tell you the story. I didn't invent anything. Philosophy of science has gone through this process a long time ago. 1948, there's a very famous paper by Hempel and Oppenheim. They were thinking about explanation and prediction in terms of logic. Nothing to do with data. Forget about data, right? Logic, the concept of prediction and explanation. And they say explanation and prediction have the same logical structure. Fight, fight, fight in the journals, fight, fight in the whole community. 10 years later, a paper by Helmer and Rescher, they conclude that it becomes pertinent to investigate the possibilities of predictive procedures autonomous of those of explanation. So after 10 years, they realized, wait, maybe we should just explore that they're different. And again, fight, 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 fight. 10 years later, very beautiful book by Dubin called Theory of Theory Building. And he says, theories of social and human behavior address themselves to two distinct goals of science. One is prediction, and two is understanding. So they went through this whole process in the philosophy of science, and they came to the conclusion that these are really two different things, and they're both necessary for science. They're not just management and profit and right, science and truth. These are two fundamental parts of science. What I did is take this whole story and say, wait a minute, this really applies to data analysis. This is what's happening in the empirical world. And let's see how that actually happens there. So to convince you, I'll have to explain why this is true, right? So why is explanatory modeling different from predictive modeling? I'll give you a few different answers. One is they're trying to attack different goals. So when you're trying to use an explanatory model, your aim as a scientist is to try and test or to quantify some kind of a theory for the average household, for the average person, for the average transaction. This is what you're trying to do here. Whereas when you're trying to build a predictive model, you're after predicting individual records. And that's a very different type of unit of interest. So when you're building a model for the average, or you're building a model for individuals, you're probably going to end up with something completely different. So that's one point to keep in mind. Who are you generalizing to? This aspect of generalizing, right? Scientific generalization. Am I generalizing to an average person, to the average whatever? Or am I generalizing to individual observations? Here's another way to think about this. Beautiful painting. I know here in Prague we have tons of wonderful museums. This is not there, I think. But this very nice painting by Van Gogh was painted while he was in asylum in a place that was just across from this village. So he was sitting there and painting and kind of going crazy and painting. Yeah? And now consider the following. Suppose that you are a historian, and this village is gone. There's nothing left there anymore. And you're trying to figure out what was back there. What did this village look like? You know, where was the church? Where was it relative to the river? Where did people live, you know, relative to places? And you're looking at this painting. This is the only data that you have. And the only hope you can have in your heart is that Van Gogh was sane when he was painting this, because then this might convey the truth that you're after. So that's the historian perspective. Now think about someone completely different. Suppose that you're someone working in the museum, and you're in the restoration department, and you get this beautiful painting, and it has a horrible white patch right down there. And what you're supposed to do is restore this and remove the patch so that it looks as natural as possible. Do you really care about where the church was relative to the houses? Or do you care more about the types of paints that were used and the brush strokes and things that are at the level of the painting itself? And this is really the difference between explanation and prediction in terms of where the data sits. When we're doing causal explanation, the data are just trying to help us get to the truth, to what's going on behind it. So we want the data to map really well to the truth. But when we're doing prediction, I don't care about the truth. I care about the level of the data. I'm going to be predicting more data like this. So I need a completely different set of tools in order to predict. So this is another analogy of why explanation and prediction are different. When I wrote the paper that's in statistical science, one of the reviewers came back and said, the first round that I sent it, he said, "I can't read your paper. There is no notation in it." And you know, the first reaction is like, but then you sit and you think about this. This is the best advice I ever got. You always put the reviews into a drawer. You lock them up for 24 hours. And when you've kind of breathed really well, you open it back up. So then you take it out. And then you say, this is a brilliant idea. And I started incorporating notation very lightly into the paper. And I realized that was the problem. I needed 2 sets of notations, which we normally don't have. I needed notation, which is the usual statistical stuff, the measurable stuff and the statistical models. But I also needed different block fonts or whatever, to talk about things at the theory level, at constructs, at a theoretical model. And those we don't usually have any notation in statistical journals. So I ended up using 2 different notations. I'm not going to bug you with any of this notation later on, but just so that you can get a feel again about this big divide, where in prediction I don't need 2 sets of notation, but when I'm doing causal explanation, I actually do. The last part there, which is the statistical model, is really where this beautiful paper by Leo Breiman, Statistical Modeling the Two Cultures, is talking about the difference between what machine learning is trying to do and what statistics is trying to do. One of them is after the F. The statisticians are after the F function, whereas the machine learning and the prediction is about finding the Ys. So that's one part of it, but it's not the whole story of explanation versus prediction. Okay. Another thing to consider, when I was thinking about explanation and prediction, I found initially 4, and more recently the 5th, aspects that really kind of help you distinguish between them, or at least understand the differences between them. The first one has to do with the role of theory versus data. Now, it's not that explanation is on one end and prediction is on the other end, but it's just that you would think about this balance in a different way. When you're doing explanation, theory is king. Data is only there to quantify stuff and test stuff. But theory is the most important thing. If you go to someone in the social sciences and take away their theory, they will not want to talk to you anymore. You can't do anything without the theory. In contrast, when you're doing prediction, data is king. You might use theory, but in a much more pragmatic way. You'll use domain knowledge, you'll be fluid about it, you'll be open to different options of the theory. So there is theory, but it's not in the same way that we saw it's used in explanation. So that's the theory-data aspect. Here's another aspect that's different, causation and association. Obviously, when you're doing causal explanation, it's all about causation. You don't want to hear any stories about association, although we saw that they do use regression models and association-based models for testing causation. When you're doing prediction, you don't really care about causation. It's all about association. If you find correlations, you're good, at least for the short term. right? Where does causation come in? Well, if you know that something is causal, you can try to put it in and see if it helps you predict. But sometimes we find that adding those causes actually makes the predictions worse. So that's kind of an interesting story that a lot of fields are finding. A third aspect is how you're thinking about the whole problem. When you're doing causal explanation, it's a retrospective analysis. You're asking a question about how does the world work? So you take a set of data and you try from there to find, did this cause that or did this not cause that? And it's retrospective in nature. Most of the time. This is most of the time kind of. When you're doing prediction, it's all about thinking forward. How am I going to deploy this model? How am I going to use this model? I'm thinking prospectively all the time. That's going to influence lots of your decisions in the modeling process, and we'll get to that soon. Fourth distinction is what the machine learners love the most, and people in statistics also love this the most because you can write it down and measure it and quantify it. It's not so abstract, is the bias-variance trade-off. And we know that when we're doing causal explanation, the biggest villain is bias. You want the painting to look as close as possible to the real village. You want the bias to be 0. And I don't care about the variance. So the whole econometrics toolkit is designed to detect bias, reduce bias, do everything you can to murder the bias. But when we're doing prediction, it's not just about bias. It's bias combined with variance. And that's where we have these special models where we intentionally, by design, introduce some variance so that the combination of bias and variance overall shrinks, and that gives us better predictive models. So we're trying to optimize a different function. Now, again, this is the one that people say, oh, yeah, I understand bias variance. That's explain or predict. No, it's just part of the story. It's not the whole story. The last aspect that is not in the paper, but things happen all the time, and I have conversations with people and discussions, and definitely the fifth one has to do with what I just mentioned briefly before, and that is that when you're doing explanation, you really care about the average, typical record. You're modeling for that. Whereas when you're doing prediction, you're generating predictions for each and every record individually, and that is, again, a completely different type of unit of analysis that you're interested in. So when you consider these 5 different aspects and how things are going to be very different, it's highly unusual that you will get a model that is both very good at prediction and explanation, because you're going to be tailoring it according to these different trade-offs. There's a very nice book by Richard Burke called Statistical Learning from a Regression Perspective. And in this book, he talks about, again, regression, of course, and he says the following: the goal of finding regression models that are predictively accurate differs from the goal of finding models that are true. There are 2 areas in statistics where people really feel this distinction between prediction and explanation. One of them is in model selection, like this book, where you have models and you see, oh, if I'm trying to choose the one that has the best predictive accuracy, it's not choosing the right one. I simulated the data. I know which is the right one. And then the other field where a lot of people feel this very painfully is in time series forecasting, because their forecasting into the future is very different from analyzing the past and coming up with what are the patterns. Other than those 2 fields, I think most other fields don't feel the pain as much and don't really think about prediction and explanation as completely different things. So my first point is going to be that if you're going to use your data and build an explanatory model, you're not going to end up with the same model that you would have gotten if you've used this, maybe even the same data, for generating a predictive model. And to show you that, I'm going to give you a few examples and then walk you through the path of modeling. So first of all, I'm finally talking to an audience who's at least not 20 years younger than me when I ask them, do you remember the Netflix prize contest? And today, nobody raises their hand anymore. How many people remember the Netflix prize contest? Oh my God, I'm so old. Okay. So this ran in 2006, not so long ago, and it was a huge contest that Netflix basically wanted to harness their non-employees to do the work for them. And they were trying to improve the recommender system because they had a really terrible recommender system at the beginning. You used to watch movies, and it would recommend something, and you'd you'd wait for the DVD to come by mail by 2 days, and you would happily take it out of the mail, put it into your DVD box, and it was a terrible movie. And people got really angry, so they had to improve the recommender system. And they decided, okay, so let's release a huge data set of 1 million rows of each row was 3 numbers. It was a movie ID, a user ID, and how much that user rated that movie in 5 stars. Okay, triplets, triplets, triplets. I don't know how to say that in Latin, triplets. And they said whoever is going to improve our recommender system by, I think it was 10% on some metric, will win $1 million US. It was a huge contest. There was a lot of progress in the whole field of recommender systems thanks to that. And the first thing that many of the teams were doing was doing something that John just was showing us how to link tables. They went and got the movie ID and went to different websites like IMDb where you have information about movies, and they collected a lot of information about who's the director, who are the actors, how much money was spent on the movie, because they thought that would help us to figure out how to predict a rating for a movie. So that was the first thing. You can go to the forum of this contest. It's still wide up there, and you can see what people were doing at the beginning. Okay, 2 years later, a team wins. It's a team that's a combination of a few different teams that teamed up together. And they wrote a very nice white paper that's publicly available online. And here's what they tell us. We tried to benefit from an extensive set of attributes describing each of the movies in the data set. Those attributes certainly carry a significant signal and can explain some of the user behavior. However, they could not help at all for improving the predictive accuracy. So you put this huge effort, you go and get data from other sources about these movies, you think this is going to improve my chance of predicting these ratings, and it turns out it's worse. Now, think about it this way. Suppose that Netflix posted this whole story not for the purpose of improving the recommender system, but in terms of a scientific question of why do people rate movies the way they do? Scientific question. That's something, right, that you might see in psychology and marketing or whatever. Then, obviously, you couldn't take this solution. You would have to get those attributes about the movies, and more so, you'd need attributes of the people who are viewing the movies. I think that was another table that you had, John, in the presentation. And you'd have to link them up so that your model would eventually use all of that information. So there's not one solution that's wrong and one is right. They're trying to answer different kinds of questions. One is trying to predict, and one is trying to explain. And you need different data to start with. One more example of where these things really come out is when we talk about bioequivalence in pharma. So when a company wants to come up with a new drug, and it's a generic drug, and they want to show that the generic is identical to a brand drug, they have to go through a process that in the United States goes through the FDA. And to show that two things are bioequivalent, and this is not my expertise, so excuse me, I know there are experts in here on this, what they do is they basically measure some outcome and compare with a clinical trial. Some people get the generic, some people get the brand, and then they compare the two groups. And if the results are within, let's say, a 90% confidence interval, then they say, okay, you know, the results are the same, you can start selling the generic. Now, this is a long time ago. In 2005, the acting commissioner of Food and Drugs said the following. They realized that this is not really predictive medicine or, personalized medicine. He said, we're planning to develop predictive models for bioavailability and bioequivalence. So the FDA realizes that what they're doing here for bioequivalence is more explanatory or even just descriptive. They're definitely not doing what everybody's talking about today, which is personalized medicine. For you, the brand is better, but for you, the generic actually works just fine. And that would be a completely different test than what's going on right now. Okay, the last convincement story that I think from here you cannot escape anymore is walking through the process that we all know of data analysis. And when we talk about data analysis, I just have a schematic that kind of walks through. We start with a goal, then we have our design, the study design, and we collect the data. We have a lot of data preparation. That's the ugly stuff that nobody wants to do, but we have to do it. And that's where JMP is probably a really helpful thing. And then we have exploratory data analysis, where we explore it and we go back. Nothing here is linear, right? We keep going back and forth and back and forth. And after we've kind of explored the data, we start thinking about which variables can we include in here, what methods, what world of methods can we actually consider. We have a whole phase where we're evaluating different models, comparing them, validating each one of them. And eventually, you're going to choose one and use it somehow, and deploy it, reports, or whatever it is. So this is the generic process, and it will be the same process if you're building a predictive model or you're building an explanatory model, but every detail and every step is going to be different. All right, so let's take a look at the different steps and see what happens. Suppose we start with a goal definition. It's either explanation or prediction. And now I'm going to have to design my study and collect the data. So there are a lot of questions that come up at this phase. One of them is, are you going to use observational data, or are you going to actually go and run an experiment? If you're after a causal question, you might opt more for an experiment, but then there might be all kinds of problems that will lead you to ethical issues or social issues, and you might end up using observational data. If you're actually trying to build a predictive model, then you might think, oh, an experiment is actually nice. We'll get nice, clean results. But many times an experiment is too clean. It's not as similar as enough to the real deployment scenario, and that's where observational data sometimes turn out to be better. But sometimes what you're trying to predict is not available in the observational data. So there are all kinds of questions that I just started a Q&A with myself. But the answers are going to be different if I have a predictive goal in my mind or if I have an explanatory goal in my mind. Next questions that people ask is, OK, should I use primary data? Should I actually go and collect these data myself? Or should I use secondary data that someone else already collected and great, they're out there already? Again, the answers that you'll have will be different if you're trying to predict or explain. For example, in a secondary data set, maybe I'm measuring anxiety in some way. Okay, maybe it's blood pressure or something like that. And that's just fine because I can operationalize anxiety and measure it using blood pressure. So I can use that secondary data set for explanation. But maybe I'm trying to predict anxiety, but I'm not, what is predict anxiety? I'm trying to predict something very specific. When we're doing prediction, it's some metric. And if the metric that I'm interested in is not your blood pressure, I can't use that data set. So whether you can reuse data or not reuse data is going to depend on what is in there relative to your goals. And again, explanatory and predictive goals have completely different structure. Another question is the instrument. How do you test your instrument? A lot of people who do surveys care a lot about reliability and validity of questions, right? There's a whole set of tests that you do. And you're really worried that people will lie to you. How do I catch them? I'll twist the question this way. I'll show it up here, there, right? Everything to trick the people to actually give you the truth. If you're trying to predict, if you're building a predictive model that will use survey data, maybe I don't care so much if people are lying to me, as long as they continue lying in the same way in the future. So I don't need to calibrate my instrument in the same way that I would if I'm building causal explanation. How much data, right? The usual question, how much data? If we're doing explanatory modeling, a lot of it is about statistical power and being able to identify the effects that we want and false errors and all that. But in prediction, it's a different story. We need a lot more data, usually because we use a lot of data-driven algorithms. We need data for holdout sets, which is a fundamental principle in prediction. And the whole story is completely different than in explanation. You can't do any power calculations for a predictive study. Another interesting question that people usually ask is, how do I draw the sample? There are a lot of different sample designs. And there's a very nice paper by David Ashartus and Jan DeLeeuw from UCLA that talked about hierarchical or multi-level data, where you have data, let's say, of students in classrooms and schools, and you have to sample, let's say you have money to sample 1,000 kids. And how do you sample? Do you go to just one classroom and sample everyone? Or do you take multiple classrooms and sample in different ones? And their nice paper shows that if you're trying to predict, it's better to increase the group size. But if you're trying to do causal explanation, you're better off increasing the number of groups. So your whole design is going in completely different ways if you're trying to explain or to predict. At this point, we haven't even collected the data. We're just designing it, and we're going to get different data at the end. All right, next step. We have our data. We got the data set, and now we're going to pre-process it. One big headache is missing data. Every data set has this headache. It doesn't exist, right? We have a beautiful set of theories in statistics about data imputation. We have to figure out whether the missingness is random or missing completely at random, or there's like the whole typifying stuff and different solutions. That is very nice if you're trying to explain. If you're trying to predict, that doesn't help you at all. And in fact, there's a few interesting papers coming out in the machine learning literature that were trying to address the missingness when you're trying to predict. There's a nice paper by Meital Sar-Chechansky and Foster Provost from NYU that talked about a different solution. Suppose that some people don't fill out their income, other people don't fill out their education, some people don't fill out their age. Instead of imputing it, you build a bunch of different models. Some models don't have age, some models don't have income, okay, and so on and so forth. Then comes a new person. If that person didn't fill in their age, you use the model that doesn't have age in it. And of course, they kind of built it in a way that's scaling, and you don't run all the possible models and whatever. But that's a solution that's very useful for prediction, but total nonsense for explanation. You'd never build multiple models for explanation and then start using this one, that one, right? It makes no sense. Another big difference is in terms of data partitioning. When we do prediction, the major thing that we do first is split the data, keep a holdout set, hide it, don't let anybody of the, no analysts can touch that until we're done with modeling, and then we can test how well the model works on new data. And that's prediction. In explanation, we don't typically do that. Some people want to test the predictive accuracy, so they'll do that. But typically, again, in explanatory models, in papers, you'll never see that happening. Many times because people have small samples, but even now that they have really big samples, they won't do that. The only reason that people will do that in explanatory modeling is if they want to test the robustness of the model. So maybe if they have 100,000 records, they'll have 50,000 and 50,000. They'll fit the model here and then check that they get the same model if they do it again. So it would be a completely different use of partitioning the data and not like what you do in prediction. Data exploration is the next step. And in data exploration, we all know that this stuff is great. We all love this. That's why we're here, right? You'll see a lot of people who are doing prediction or exploration using this type of graphics and exploration and freeform. But if you're doing explanatory modeling, you don't want to look at that stuff. You have your charts down there that tell you what to look at, which are the variables to look at, and which correlations to look at. And it really drives the way you look at your data. And that's why you will not find any exploratory charts in social science papers. And if you do, you'll find summary statistics, one table or something like that. Because theory tells you what you should be looking at. You don't just roam around. They call that data fishing. Another interesting thing is principal components analysis, a very important part of the exploration toolkit. When we use it in prediction, we use it often for dimension reduction. We can't do clustering or any kind of distance methods when we have these huge multidimensional data sets, so we use it to shrink. I don't really care what happens, I just want the shrink. When we use PCA in explanatory modeling, it's very popular in psychology and whatever. They also use PCA, and then they put a cherry on top and call it factor analysis. But what they care about is they're using it so that they can better understand what are the underlying constructs. Oh, these three questions bunched together, they're measuring the same construct. So they're looking for something completely different coming out of the PCA than what we're using when we're doing prediction. Completely different. So I might even choose a different number of factors or do different rotations or not do rotations at all, etc. Next step is choosing your variables. Okay, so now I have a bunch of variables and I have to choose which ones are going to go into my model. Think of a regression model or something like that. Causation versus association. Again, if you're theory-driven explanation, your theory tells you which variables must be in there. If you have some additional stuff, gender and this, you could put it in and it's called control variables. They're not interesting, they're just control variables. Whereas when you're doing prediction, you just try lots of things because you're looking for the ones who are most correlated and associated with the outcome of interest. So the way you're thinking about things is different. I did a lot of work on eBay modeling at the time. We were looking at forecasting the price of the auction at the end. And there's wonderful theories from game theory about what is the price of an auction as a function of a few things like the number of bidders and the starting price. And those are very nice theories. They can explain very nicely how price is affected by number of bidders, for example. But when you're trying to build a model to forecast the final price in an eBay auction that's just about to start, I don't know the number of bidders. I will only know the number of bidders once the auction closes. So this idea of having variables or predictors that are available at the time of prediction is fundamental in prediction, but is not needed in explanation. I can use the same worksheet with the data, right? I have the worksheet, number of bidders in this auction, I can build a model, but it will be a useless predictive model and a good explanatory model. What explanatory modeling cares about is this notion of endogeneity or reverse causation. There the theory tells you, listen, be careful. Some of the things that might be correlated with your outcome might also be, the outcome might be also causing them. So it might be going around. And that is a bad model. You cannot do that. And that's where the reviewers will shoot you down. You have endogeneity in your model. So it's a different concern about which variables are allowed to go into the predictor side. Multicollinearity, we're famous in statistics for really scary long words. That's one of them. You have to find it, identify it, get rid of it. Terrible problem when you're explaining. When you're predicting, unless you're really needing to extrapolate very far from where you are, it's not a problem. Here's another one. Main effects and interaction effects. Well, my undergrad was in statistics and in psychology, and I remember they taught us in psychology, if you have an interaction term, you always have to have the main effects. Otherwise, the model is not identifiable. In terms of the theory, you can't interpret what's going on. But when you're doing prediction, if the interaction is helping you, but the main effect is actually deteriorating the predictions, you just knock it out. We don't really care about identifiability. So all these will lead to a completely different set of predictors that you'll end up having in your model if you're trying to predict or trying to explain. Remember the bias variance story. That's going to lead to a lot of choices in terms of models and methods that we're using. When you look at the types of statistical models that are used in the social sciences, in explanatory work, you will see regression is by far the most popular. You'll see path models like the ones I've shown you before. You will not see things that are like shrinkage models, ensembles. You will never see those because those models by design introduce bias in order to reduce the overall bias variance. That's why they won't be there. It doesn't make any theoretical sense to do that. Why would you make your model biased on purpose? So shrinkage models and ensembles are wonderful tricks for prediction. These are like the best tricks to win any competition, right? But they work really badly if you're going to do explanation. I just want to make a note here about one confusion that people have. They say, okay, so you mean explanation is that I'm fitting a predictive model, but I can see which predictors are in there, like a tree. A tree is an interpretable one. So if I use a tree, I'm explaining and predicting. There's a big difference between explaining and being able to interpret your results. A tree is a predictive method, and you can explain which predictors went into your story, but it doesn't give you the causal explanation of what's going on. And that is the big flaw behind sentences like we saw Deloitte telling you that we can also explain why these people are leaving. You can't explain. You can just tell me which variables were in your model, and that's a completely different story. Okay, now we finally reached the stage where we have a bunch of models and we're testing them and we're trying to compare them and validate them and choose which one is going to be the one. And this whole process is going to be a little bit different if we're predicting or explaining. When we're explaining, there are 3 layers. We have the theoretical model, right, the theory. And then we have our empirical model, the statistical model that we built. And then we have the data. Us statisticians, we kind of focus on the empirical to data part. And that's where we do a lot of residual analysis and testing hypotheses and things like that. But there's also a very important piece, which is the validation between the empirical model and the theory model. And again, you'll see that in those kinds of papers. Why did you use this regression? Why are you using this path model? How does it map to the theory? And it's not a simple answer. It really is not simple. So every one of the models that you're considering has to go through these dual filters in order to choose the ones that are adequate. That's why you'll also see in lots of papers in economics, I see this a lot, they'll have a bunch of regressions that they ran, and each one of them will have a different subset of predictors. Some of them will be nested in others, but they'll show you all of them. And a statistician will say, take that one out, there are insignificant effects there. No, I need to see all of them because theory was telling me something about those insignificant effects. It's a different way of presenting the results as well. When I'm doing prediction, that first layer doesn't exist. So what I have is my empirical model on one side and the data on the other side. But I think about the data in 2 different ways. I have the training data where I fit my models, and I have the holdout data that the models never saw those data. And when I do my validation here and decide what is a good model and what's not a good model, I'm looking at both relationships. I'm looking at how well my model fits the training data, and I'm looking at how well it fits the holdout data, how well it predicts the holdout data. And for example, if the performance on the holdout data is dramatically worse than how well it's working on the training data, that's an indication that I'm overfitting my data, and that's very, very bad. That's the worst thing you can do in prediction. Okay? Overfitting is the biggest danger in prediction. It's not the biggest danger in explanation. Okay, finally, you get your final model. How do you use it? Well, if you're using this for an application in industry, then if you were doing causal analysis, then you've identified these causal factors that you really care about. You'll change them, or if you can, if you have control over them, or if not, at least you'll know what's going on. And usually you'll use inference, and you'll have this whole concept of a null hypothesis, right, which you're rejecting, or if you're Bayesian, you have a different world. And if you're doing prediction, then you would use your model in a completely different way, right? You would actually take this predictive model that you built and deploy it and start predicting whatever you're trying to predict. So that's the usage, which will be completely different. If you're doing scientific work, if you're writing a methodology paper, if you're writing, I don't know, some kind of a journal paper, then the final result will be used in a slightly different way. If I'm trying to test causal theory, then I would actually have a paper that writes whether, yes, I refuted or not refuted this theory or not. If I'm trying to predict, I can't just give you predictions. No paper will publish a set of numbers because that's not really what they care about. But this is where the major question that my colleagues were asking me about, so how do we use prediction for science? And we wrote a separate paper that explains about, these are 6 different ways that you can use prediction for developing theories, comparing theories, improving theories, testing theories, and these are not possible to do in the same way using the explanatory toolkit. Hello. Oh, okay, yeah, so that's the paper down there. Okay, my second point is much, much shorter, and that basically says that once you have a model, and I don't care if it's an explanatory model, predictive model, whatever it is, if you measure its explanatory power, if you measure its predictive power, you can't say anything about the other one. They're just completely measuring two different things. And when we talk about explanatory measures, these are the typical ones that people use, p-values, R-squares, goodness of fit. And the biggest scary, risky thing are your type 1 and 2 errors that people are always afraid of. Whereas when we're doing prediction, we use a completely different type of metrics. First of all, we look at out-of-sample metric, those holdout metrics, and we care about prediction accuracy. Sometimes costs come into play. If you misclassify this way or that way, it costs you differently. We're comparing the training versus the holdout, and the biggest danger there is not type 1 or 2 errors. I seriously don't care about them. They don't exist there. I care about overfitting. So we're, again, optimizing for something different. We're using different measures. They're computed from different places. You can't use the same metrics and say, oh, my R-score was high, so I'm explaining and predicting. It doesn't work. This picture kind of shows the idea that explanation and prediction, the power, is not 1D. And this was a good input that I received early on when I was presenting this paper, and I had a long discussion with people. At first, I thought it was one dimension. Explanatory power is here and predictive power is here, so your model is going to be on this continuum. But actually, no, it's kind of more of a 2D. And if you think about grand theories, really big theories, they can be very useful even if they're good on one and low on the other. For example, remember the days when we thought the world was revolving around us? We were kind of in the middle and everything else was kind of... We know it's wrong today. So this model has very low explanatory power, but until very recently, until we had GPSs on every little thing that we walk with, navigation at sea was using calculations based on this theory. Not because they thought it was true, but because the predictions worked much better than the true theory. It was computationally much simpler and whatever. So this is a grand theory. It has very low explanatory power, but it had very nice high predictive power. On the other hand, think about a different theory, right? Evolution, how we're moving ahead. This theory has very high explanatory power. Some people don't like that, but has very high explanatory power. But if you can predict what the next person's going to look like, I think we can't really. This theory doesn't really tell us what the next one, not the one with the Google Glass or all those. We don't know. So grand theories don't necessarily have to be able to explain and predict everything. They're very useful if they can do one or the other. And if we can map the theories in a certain domain on a scatter plot like this, then at least we know where the domain is right now, where it's going, where it's coming. Okay? So this is a very useful chart. So the predictive power of an explanatory model is something that I've been trying to advocate a lot to my colleagues, even if they don't do predictive modeling. Just take your explanatory model. Tell me how good it is. It doesn't have to be good predictive, but just tell me if it has any predictive power so that we can start assessing what's going on and understanding what needs to be developed or not. So the 2 points I made are a best explanatory model will not be the same as the best predictive model. I hope you're convinced you'll never end up, even if I give you the same data set with the same models. And point number 2 is explanatory power and predictive power are not the same thing. I hope you're convinced. If you are convinced, then there's going to be a very interesting thing that's going to come up here. Ron will talk a little bit more about this tomorrow, but this is very related to the notion of information quality or the potential of a particular data set to achieve a particular goal using a given empirical analysis method. So we have, we'll talk about this more, and we also have a book signing, so you can come and talk about this more. But the idea that the analysis goal is really going to drive everything, you can't kind of put it in isolation and just do your analysis. You won't get the same result. Okay, so finally here are the implications. In academia right now, and I'm talking about the social sciences and management, every possible field that's working with behavioral data, theory-based explanation is really the king. They don't appreciate prediction in most places except for applications, and now you can get grant money for that, but they don't appreciate it for scientific building. The distinction is blurred. Most people don't understand the difference between these two things. And those who are, want to do this usually don't have the toolkit. They don't know how to do predictive modeling. It's not taught anywhere. It's definitely not taught in statistical modeling. Remember the philosopher of sciences from back then? So in 1959, Helmer and Rescher wrote, while the value of scientific prediction is beyond question, the inexact sciences do not have the use of predictive expertise well in hand. We're now a little farther into the future, and I think this is still kind of the case. So this is a place where education really has to play a role. And I'll remind you again that Parson thought that we really shouldn't be doing prediction, forget about all that. So I think education really has to change. The biggest question that remains here is why and how to use prediction for scientific development. And beyond, again, projects and industry and useful stuff, everybody realizes that's very useful. But how do we use it for scientific development? And, this paper that I mentioned earlier on, which is a sister paper to Explain or Predict, which is in MIS Quarterly, talks about these 6 different ways that you can use prediction for testing theory, developing theory. And if you don't do it, you kind of lose all these wonderful tools that can help you develop theory. At the same time, in industry, what do we lose if we don't understand that these 2 things are different? So first of all, in industry, there's a lot of data-driven. All the big data revolution that's going on is about data-driven predictive modeling. And I think prediction is a little bit overappreciated right now. Everyone's so excited about, oh, we can do this, and the software is so cool, and we can do it. It's easy, and we're getting it, and we have, right? It's very easy. But the distinction is really still blurred. People are doing A/B testing in lots of companies, but A/B testing is not what I showed you before. Not explanatory modeling. It's a very specific kind that can do something very specific, but it's not the theory building type of causal explanatory model that I've been talking about before that. And if you think about this is the equivalent of Amazon in India called Flipkart, unless Amazon is able to kick them out. Flipkart has a very big problem, as many e-commerce companies do in India, and that is that a major mode of payment is they come over and you pay them on the spot. Okay, no credit cards. A lot of people don't have credit cards. So a big problem that these companies have is that the guy goes to deliver, and they arrive at the customer's house with a good, and the customer doesn't want to pay them. So there goes the transaction. So a big question that they want to ask, you could use analytics with this guy's going, is like, will the customer pay? And if there's a high probability they won't pay, maybe you can call them in advance. Maybe you can, when they're doing the transaction, force them to use a credit card or something like that. But that's a fundamentally different question from what are the causes of non-payment? Why are people not paying? And that's a completely different type of modeling that you would have to do. And again, DOE is not going to solve your problem here. You really need to go back and have some theories of human behavior and understanding of what's going on. So this is kind of different. And if you keep thinking that you're doing explanation and you're not, then what you're having at the end are these very short-term solutions. Yeah, prediction works great, but for the short term, but you don't really understand the causes of what's going on. And at the end of the day, this is causing a lot of ethical issues that are happening now that are popping up in every possible area that you can imagine. Every company is now facing this. And academics, we're all sitting there and like holding our heads. We don't know what to do. So I think we have to think a little bit closely more about what it means to do prediction. What does it mean to do prediction without understanding enough what's going on, and what's going to happen if we keep doing this? And the major question is really, so how do we actually incorporate theory-based explanatory modeling, which takes a lot more time and resources than the fast predictive type of modeling, into the type of industrial work that we're doing right now. There's a paper that was published recently with responses and a rejoinder about analyzing behavioral big data. And you can take a look at that, and I'd be glad to hear any feedback on that. And I'm going to stop and say that, again, whether you're doing applications, industry, or you're doing theory development, you're going to have to do both explanation and prediction. You're really not seeing the world as it is, and you're not grasping what's going on and using it to the best utility if you don't realize they're different and utilize both of them. So I'm going to stop here and just leave a bunch of papers up there.
Thank you very much. Appreciate it. Unfortunately, we don't have any time for questions, but Ron and Galit will be in the foyer tomorrow at lunchtime for a meet and greet. And if you've got one of their books, I'm sure they will be happy to sign it at that time and also engage in whatever questions. They'll both be around through the conference, though. If you spot them, feel free to ask some questions. Now, we have got a lot coming up, and we really take off running now, because there are 24 breakouts over the next day and a half. They run 4 at a time. So you have some tough choices to make. You will want to use your program or the app to help you make those choices. This afternoon, don't forget, we will be having the poster presentations during tea. They will be out in the foyer. And don't forget also to rate the papers and posters that you attend so that we can give away those awards tomorrow afternoon. Before all of that happens, however, is lunch and the Discovery Expo. Remember, Discovery Expo is your time to talk with our developers, preview the posters. Don't forget Jump Books and Training and their giveaway. You'll want to drop a card in over there. At lunch today, which will be downstairs in the Midtown Grill, everyone's invited downstairs in the Midtown Grill for lunch. At lunch, you will find a few tables with some tabletop discussion topics. If you have an interest in any of these, please note the one that you're interested in there on the screen. Find a table with that topic, sit down and have a conversation with others who are interested in that topic. These are not guided conversations. These are whoever sits down, start talking about whatever area you're interested in. If you're not interested in any of these areas, sit down at another table, introduce yourself to whoever's there, and have your own conversation as you will. A special note about tomorrow's lunch. To be clear, this is tomorrow's lunch. We are having a users group leaders luncheon. We've got a number of leaders of Jump users groups from around the area who will be having lunch together and discussing best practices in users groups. If you have an interest in this and have not signed up, we do have a few seats left. You can sign up at the registration desk. If you're interested in forming your own users group in your region or at your organization, we would love to have you join us. Again, sign up at the registration desk. There are just a few seats left for that. All right, tonight, we've got another great event for you planned. We will be going to Smetana Hall at Municipal House. Now, this is a very historic building. Lots of history has been made there. Don't know if we're going to make any history, but the Prague Chamber Orchestra will be playing for us tonight. So you will want to join us there. We will leave for a short walk. It's only about a 5-minute walk from the hotel. We will leave from the hotel in the lobby at 6:45 tonight. 6:45, that's 18:45 if you prefer. But that's tonight. Join us there. Short walk to dinner. It's going to be great. And for right now, go enjoy your lunch, enjoy Discovery Expo, and then breakouts after that. Thank you so much.